Okay.
Good. So now we are very happy to have Lampros Lamprou, who will tell us how to go inside the hologram.
Well, thank you. I'm very happy to be invited to give this talk. I will be presenting some work that I did with Daniel Zafaris that we reported in this paper over here earlier this year. And there are ongoing discussions in collaboration with both Daniel Zafaris and Jan de Boer. So Daniel and I wanted to understand how to reconstruct the experience of an observer that lives in the bulk of ADS. So of course, this observer is a subsystem of the CFT. And this question of how to take the perspective of a subsystem of a quantum theory is not something that we traditionally ask in quantum mechanics. The formalism is not designed to directly apply to this question. So we have to think a little bit about this. And we won't, of course, resolve the general question of how you see a quantum theory from the inside, but we'll make some progress in ADS CFT. And the motivation is not academic. We're motivated by the reconstruction of black hole interiors. So imagine an infalling observer. So clearly the question of what's the state of the bulk field theory behind the black hole horizon, is there a smooth spacetime, what's the expectation value of the stress tensor, and so on, are operationally meaningful questions about this infalling observer. And we would like to, and given sufficient input, we should be able to answer that question, at least in ADS CFT, where we have some understanding of the quantum system. Questions that we would like to ask, for example, is how much proper time this observer measured before they hit the singularity, or perhaps before they met some other observer that jumped in earlier, or from the other side in this two-sided black hole setup. Another related question is if I'm carrying a Geiger counter as I'm crossing the horizon, do I measure any energy along my trajectory? And of course, a more refined and ultimately interesting question is what CFT operators describe my experience behind the horizon? What are the degrees of freedom that I can measure and couple my devices to? So there are many ways of trying to approach this question of the interior reconstruction. We decided to take this operational approach and try to understand what it means to propagate, to evolve the system with this proper time Hamiltonian along a physical probe's word line. So what is the operator in the CFT from some first quantum mechanical principles? What is the operator that generates this internal clock of the excitation as it moves in the bulk? So our goal, ultimate goal of this talk, will be to learn how we can make progress towards switching to this infalling reference frame. And there is a little conceptual puzzle that, at least for me, was a big part of the motivation of starting this work. It's most sharply posed in this two-sided black hole setup. Here we have two CFTs, holographic CFTs that are dynamically decoupled from each other, but we start them in this highly entangled state, the thermofield double state, describing this short wormhole in the bulk. And in this setup, we can introduce some kind of physical probe entirely on the right-hand side of the theory by acting with some operator of element of the right CFT algebra. But since this operator, the two theories are dynamically decoupled, clearly no amount of boundary time evolution will ever mix this operator with the left. However, we do see that in the probe's reference frame, after some finite amount of proper time evolution, according to this diagram, I am behind the black hole horizon, which means in causal contact with the left, and now I can receive signals from the left, which means that the proper time evolution of this guy necessarily must couple me to the left, so that I do not commute with operators of the left CFT. So this is a sort of conceptual puzzle in the sense that we built a probe out of right CFT degrees of freedom, and yet in the probe's own reference frame, there exists dynamical coupling between left and right. Now, since we're not free to choose this, what this Hamiltonian is, rather it has to be derived, somehow we are led to the conclusion that in some way, the entanglement structure of the initial state that I fed the system translates in this internal reference frame to a coupling term between the two bulk exteriors. So we would like to understand in what sense and under what conditions this thing happens. Now, we will not start, of course, from this black hole setup. We will return to this question at the end. We will start from a simpler setup where we introduce a physical observer in the bulk in some space-time which does not contain black holes. We will evolve the system from some initial slice to some final slice. And then the first question, the first step that we would like to make will be to extract the physics in the reference frame of this probe. But the key here to remember is that we want to extract the physics in a universal way. And what I mean by that is without making reference to the solution for the bulk spacetime that the probe is propagating in. We would like a prescription that can be entirely formulated and answered directly in the CFT using properties of the probe alone and not without inputting, let's say, what the metric of the bulk is, as more traditional reconstruction techniques do. And again, what we will be interested in is measuring the proper time along this trajectory and the amount of energy flux that the observer measured in the frame. So this will be our first step. Okay. So we first have to decide on what kind of physical probe we'll use as an observer for our purposes. So we will use a black hole. We will choose a black hole, in particular a black hole entangled with an external reference as our probe that we will use to explore that spacetime. And we will do this in the following way. We start with a CFT, which we will call the system, which holographically describes the universe that we want to explore. And then we also assume a copy of that CFT, which is the reference, and we will not do much with it. And we initiate the two CFTs in the thermofield double state. This describes on the system side an ADS spacetime with a static black hole sitting at the center. So what we will do then, after that, is we will apply on this thermofield double state some amount of ADS translation so that we shift this black hole away from the center of ADS, close to the asymptotic boundary. This is an action of one of the symmetries of ADS. And then on top of that state, we will act with a unitary on the system side, whose role is to generate whatever background we want to explore with our probe. It generates the space-time and the excitations, and we assume that it acts at a space-like separation from the place where I initiated my probe, close to the boundary. And then we will evolve this system with the dynamical Hamiltonian. The corresponding state describes, of course, the evolution of the system, which in the bulk looks like the black hole propagating in this space-time I generated in this way. And if the features of the space-time are larger than the size of the black hole, then to some good approximation, the black hole will follow the waterline of an ideal GR observer in this space-time. So this is the main setup. And let me immediately address two frequently asked questions. The first one is why use a black hole in order to describe this observer. So remember that when we talk about observers in the general theory of relativity, we always approximate them with, we always treat them as idealized, localized probes. We don't need to make specific statements about what the observer's device are made of. We simply keep track of only their kinematical state, the state of their kinematical variables. And that is sufficient for the questions that GR wants to answer. So we were looking for a similar kind of idealization in this case, some sort of the most economical or the most universal kind of probe. And if you're looking for an idealization of an observer, a physical observer of some given mass, the most economical thing to do is to replace them with an equal mass black hole. So in that sense, it's kind of like declaring a maximal ignorance, fixing the mass of the physical probe, and declaring maximal ignorance about what the probe is made of or what's its internal state. So in that sense, the black hole is a good classical probe for the spacetime that we can hope to use to extract universal aspects of the universal experience of any observer moving along a world line. Another thing is that black holes serve as, oh, there's a raised hand.
Yeah, Mukund, go ahead.
Yeah, Lampros, just to make clear, you want this to be a probe. So are your black holes in some sense small? You don't want them to back react.
So they will back react, they will necessarily back react as any physical probe will, but the size of the probe is actually the second frequently asked question, and I will make a comment on that in just a moment. Thanks. And so another reason why the black hole is a good approximation for an observer is the fact that it serves as a particle detector with a universal response. And whenever particles cross paths with a black hole, they will get absorbed, assuming they're small enough. And the response of the black hole will be an increase of its size. This will play a role in our formalism. And the third benefit of using a black hole is that I can create this state, I can introduce that probe using reasoning, using only CFT reasoning. I don't need to make specific assumptions about the structure of the bulk. I simply need to initiate my state in this kind of thermal state, and that will be sufficient for introducing a black hole and observer into the system. So it's very simple. It has a very simple description in the CFT. Okay, so this is why a black hole is a good proxy for what this observer should be. The second question is, okay, I created my black hole using the thermal field double, which means that I described a canonical, a black hole in the canonical ensemble on the system side. Yes, Raphael.
Hi, sorry, yeah. I'm just curious, in the real world, a black hole that interacts with matter will start spinning up. Is that relevant? Do you include that effect in, or do you treat this as a Schwarzschild black hole the whole way?
So in the, this will not change the formalism, and actually I can point at the place where the spinning of the black hole would be relevant. But in my approximation here, I will not deal with this type of issue, but I don't think it poses a restriction for the formalism.
Thanks.
Well, in the strict formalism that I will describe, the angular momentum will be zero, but I don't think it's a fundamental problem to extend it. But we can discuss this later. Yes, so I introduced my black hole using the canonical ensemble on the system side, which means that my black hole are cosmological size at least. So these are big black holes, so not exactly probes. Well, they are probes if the features of the spacetime are much larger than an LADS scale. So in that sense, these big probes can be used for this type of for probing sub ADS structure. I'm sorry, super ADS structure. But this doesn't seem to be a fundamental restriction of the formalism for the following reason. There is also the possibility of projecting the thermofield double state onto a microcanonical window, namely a window of an energy window of smaller width than the canonical width, by simply including some kind of envelope function here in this superposition. And these microcanonical black holes can actually be made much, much smaller than LADS, in fact, parametrically smaller. Their horizon radius over the LADS radius goes to 0 in the large N limit. So now we didn't analyze these black holes in detail, and there are some subtle issues with using those small black holes for probing the spacetime. But there seems to be, the size of the black hole doesn't seem to be a fundamental restriction of anything I'm about to say, and these black holes can be made smaller. For the purposes of the talk, I will focus on the big black holes because everything I write is simpler. Okay, so okay, another raised hand, Veronica.
Just a quick question. I mean, since you're wanting to figure out what's the proper time, there isn't a natural notion of the proper time of the black hole, or if you had a bunch of observers around the black hole, you could make the proper time arbitrarily long by the redshift. So how do you retain that? Or should I just
Good. So I will ask you to wait for a couple of slides, and I will explain exactly what I mean. Thanks.
Okay.
All right. So this is the setup, and I hope it was somewhat clear. So now let me explain the problem we're trying to answer. Now, clearly, it doesn't make. We want to ultimately learn how to generate the Hamiltonian of the proper time of the probe, an operator that moves us along the word line of this propagating excitation. In this case, a black hole. But of course, it's not really meaningful to talk about propagation in proper time of observables very far away from the black hole, since there is no kind of preferred slicing of the universe in the frame of that world, of that black hole. So instead, we will focus on operators which we will call the atmosphere operators, operators very close to the black hole. So imagine some little tube around the black hole's word line, and there's some region of some radius which is comparable to the horizon radius, within which the local operators inside this region, we will call them the atmosphere operators. So what we will call the proper time evolution will be precisely the unitary that maps operators from in the atmosphere of the black hole at some given initial slice to the atmosphere of the black hole at some given final slice. So this operator, which we will denote as V for the entirety of this talk, that maps initial operator algebras in the atmosphere to final ones, we'll call, of course, the proper time evolution. A quick comment about these operator algebras. These operators will be framed to the apparent horizon of the black hole. We're interested in describing physics in the frame of this excitation, in the frame of the black hole, and therefore the natural way of kind of labeling these operators is with respect to their geodesic distance from the apparent horizon of the black hole. So this is what these operators are addressed like. Okay, so our goal is to learn now what generates these V, and read off from this V the proper time and the energy measured along the word line. This is where we're heading towards.
So sorry, I have a question. So these operators that you had here in the top line,
yeah.
the SD, so they involve some bulk evolution, right? So they are.
Yeah, so if you're interested in these operators everywhere along the trajectory, they involve, yes, sure, yeah. Mm-hmm.
I mean, why wouldn't we say that the unitary that relates these two is just the total time evolution, the just boundary time evolution of the full system?
So because the black hole is moving as we evolve the system as well. So what we mean by the operator algebra, of course, the operators, okay, let's take the Heisenberg picture, right? So, okay, there's two ways of looking at this problem. The issue is that the black hole is, let's take the Schrödinger picture, actually it's clearer in this sense. Then the state evolves, the black hole moves, the black hole in the new state is at a different location. So the algebra of operators that describes the near horizon operators, these atmosphere operators, will be a different operator subset. So we have to keep track of the propagation of the black hole in order to implicit in this operator, in this set of operators that I'm describing here, is that they are near the black hole, wherever the black hole is at that given time. So we have to keep that, take that into consideration as well.
Okay, thank
you. Javier.
Oh, hi, yeah, but just to continue with the question, so imagine that the black hole is just at the origin, and then you don't have to keep track with that movement. Then I think it's true that the unitary V would be the Hamiltonian time evolution of the boundary, no?
Yes, yes, certainly. Yeah, I had in mind more general situations. I agree. If you're in a static case, then of course the thing that propagates you along the black hole world line is the the CFT Hamiltonian.
Thanks.
So, okay. So this is the question. How do we extract information from this unitary V, or how to generate that V? So, so here's how we're gonna do this. So there are two natural clocks in this setup for the system. One is the boundary clock, the dynamical clock of the theory, the boundary Hamiltonian, which generates asymptotic time translations. The other one is the modular clock, generated by the modular Hamiltonian of the system, after I trace out that reference system that my black hole is entangled with. This is, of course, defined in terms of, roughly speaking, in terms of the logarithm of the density matrix of the subsystem, of the system, after we traced out the reference. And for this class of states that we're exploring, this will be a unitary, this will be unitarily equivalent of the dynamical Hamiltonian H. So the dynamical clock, the actual Hamiltonian, generates asymptotic time translations. The modular clock, in sufficiently simple situations, generates Schwarzschild boosts close to the black hole horizon. There's a way of making this precise to the extent that the atmosphere of the black hole is undisturbed. Namely, the geometry can be approximated by Schwarzschild or Schwarzschild. And the state of the QFT state in the atmosphere is in approximate thermal equilibrium, local thermal equilibrium, then this modular Hamiltonian can be argued to generate that Schwarzschild boost close to the black hole horizon. But this Schwarzschild boost maps to the proper time generator of the ideal worldline observer. Namely, if I zoom out of the figure, the black hole looks like a probe with which kind of perturbatively affects, deforms the space-time around it. And the neighborhood around a worldline looks approximately flat. Namely, there exists a local, approximate local Poincaré symmetry. One of the time-like killing vectors of that Poincaré symmetry that preserves the observer's worldline is precisely what we call the proper time. But that proper time killing vector gets glued as we approach closer and closer to the black hole horizon, gets glued to the Schwarzschild time killing vector in the black hole spacetime. So in that sense, the boost variable close to the black hole horizon maps to what we would traditionally call the proper time of an ideal observer traveling along the same geodesic. I hope this addressed Veronica's question.
Yeah, it's just distance dependent, but otherwise, yes.
Yeah, so the question is, in what sense, this is ultimately what we're interested in, right? What we traditionally call the proper length of a GR worldline. And now we have substituted this ideal observer with an actual physical probe. So we have to make a matching between what we previously meant as a proper time and now with this with the properties of this physical probe. And I'm just saying that the Schwarzschild time maps to what we originally called the proper time. So, okay, so this means that at least in these simple setups, modular flow generates that proper time. But of course, the atmosphere of the operators will not always be undisturbed. There could be matter that passes through or falls in my black hole and disturbs the atmosphere. So proper time is not literally generated by modular time in general. There are corrections to it. And it is important to understand these corrections. So in fact, this is exactly what we did. And this is the main formula of the paper. And let me explain it for you. So the idea is to take this operator V that we're interested in, expressed in the Heisenberg picture. This is what this little h is for. And take its logarithm because we're interested in the generator of that guy. And decompose it in the eigenbasis of the modular Hamiltonian of the initial slice. By eigenbasis, I mean in the basis of eigenoperators, operators with definite modular weight. Of course, one such operator is the modular Hamiltonian itself, and the coefficient of this guy in this expansion will be the proper time for reasons that I was just going over. And there could be other zero modes meaning other symmetries of the local state in the atmosphere, which is, for example, some amount of rotation about the black hole axis. But besides these two, the main claim is that most other corrections to this generator of that proper time clock give rise to effects that are exponentially decaying in proper time. The reason for that is very simple. Any disturbance, these corrections to the proper time flow come from the fact that particles may enter the atmosphere and disturb the thermal equilibrium of the fields in that region. But any local disturbance of that type will eventually get absorbed by the black hole. In the CFT, this means that this, of course, maps to quasi-normal mode decay. So all these little excitations that spoil the correspondence between modular flow and proper time flow die off in a time scale of order the thermal time. So if we wait a little bit, if we wait just 1 second, Jorge, if we wait just a little bit, a couple of thermal times after the last particle fell in, then these effects go away. The only effect that remains and persists is, of course, the fact that because of this absorption of the excitations, the black hole got fatter and the horizon grew bigger. And this effect is can be nicely captured in terms of one single type of contribution, the contribution from these operators G of omega, which I call the scrambling modes. Scrambling modes are operators with an imaginary eigenvalue, with an imaginary modular eigenvalue, minus 2 pi I. This means that they're operators that grow exponentially under modular flow. And in fact, according to a bound that Jan de Boer and I argued for last year, following work by Tom Faulkner, Min Lee, and Hua Zhou Wang, this 2 pi, this magnitude 2 pi of this modular weight is actually the maximum modular weight that can appear in this type of expansion. So the overall claim is that the persistent effects relevant for the generator of this proper time is effectively generated by the modular Hamiltonian with a coefficient proportional to the proper time, and plus corrections from these scrambling modes, these maximal modular chaos modes, whose coefficient F is a function of the energy distribution that got absorbed along the trajectory. That's because this is that's because the role of this G's is precisely to account for the increase of the horizon radius. And this coefficient precisely measures the amount of energy in distribution in a way I will make a little bit more precise in the next slide. There's a question though by Jorge or
Hey,
George.
how, how important it is that the decay in tau is exponential?
Well, it's convenient.
Because I mean, for at least for a Schwarzschild ADS black hole, we know that generic perturbations only decay logarithmically with time. Individual quasi-normal modes might decay exponentially, but if you add them all up, it only goes as 1 over log tau.
So, okay, yeah, good question. So the important thing is that the other effects are transient. So this is, in a sense, the moral argument I'm making is that if you are not interested in transient effects, but only on the persistent effects, then the only two things that are relevant for propagating this proper time is modular flow and this scrambling mode flow.
So you just need them to decay.
Yeah, so the decay is the, if you want, the important thing. The fact that it's exponential is certainly convenient and works with the various timescales. In that, you know, there's a clean separation between the decay of these transient effects and the validity of this formula, which is the scrambling time. So that's yeah, and I should actually emphasize this, that this is supposed to be a formula that in its current form is expected to hold for the scrambling time for an amount of proper time less than the scrambling time of my probe black hole. So yeah, that provides a nice clean separation between these time scales, but the decay is, if you will, the important thing. Okay, so this was the main claim. I want to very quickly, very briefly explain this correction that I was trying to illustrate here. It's actually very simple to understand with a picture. Here I have drawn my system black hole on the right and the reference that I'm entangled with on the left. And I initiate my system at this initial t equals 0 slice, but now I have included some sort of unitary excitation that introduces some particles that are bound to fall in my probe black hole. This will increase the mass of the black hole, and as Stanford and Schenker taught us, following the old discussions by Tuft and the Verlindes, in order to glue this bigger black hole spacetime into the smaller black hole spacetime, I have to include a relative null shift between the horizons of the two spacetimes. This null shift is can have a non-trivial profile along the horizon, which depends on the energy distribution that on the null energy distribution of the infalling matter, and of course it is nothing else than these Shapiro delays that people talk in the setup. So this means that because of this effect, an atmosphere operator, which you remember is dressed to the apparent horizon, which means initially dressed at some fixed geodesic distance from the RT surface, as we propagate them in proper time, it must follow this kind of trajectory here, this red arrow that I drew, where this null shift across the shockwave is precisely a result of the shift of the apparent horizon of the black hole. Of course, there are transient effects for an order beta region around this shock, but we are not interested in this. Okay, so this is what the proper time should look like, but on the other hand, you can argue that what modular flow looks like, on the other hand, is in term given by this gray arrow, namely it propagates the field in the future while holding the proper distance from the original RT surface fixed. So you see that the mismatch between the modular flow and the proper time flow is precisely this null shift, and the proper way of accounting for this effect is to precisely to include this scrambling mode correction. So this is kind of a justification of the formula that I showed you. Now, at this point, I want to pause and emphasize the aspect of this formula that I find most interesting. And this is the fact that within its regime of validity, it is universal. The objects that appear on the right-hand side of this expansion do not require as input any bulk information. Any information about the structure of the ambient spacetime on which the black hole propagates in. They are derived by only using information about the structure of the local neighborhood of my probe, but not of the ambient space I'm propagating in. Namely, both the modular Hamiltonian, the modular Hamiltonian is defined using at the initial state. So all I need to define it is the initial state and the type of probe that I introduced. And the scrambling mode is defined with reference to that modular Hamiltonian. All information about the ambient spacetime is in turn encoded in these coefficients, which I'm trying to extract. So the proper way of using this formula is to say, if I introduce a probe somewhere close to the boundary at some initial time, let it propagate, and then regain access to that probe at some later time. Construct this unitary V that maps one atmosphere algebra to the final one, and then you can reconstruct the history of that guy by simply decomposing the logarithm of V in these modular eigenbases, and read off the appropriate coefficient to read off proper time and energy distribution. So this is the main result, and you can check it. I don't have time to go through these in detail, but you can check it in simple situations like pure ADS or black holes propagating along geodesics in pure ADS or along accelerated trajectories in pure ADS and so on. I want to kind of return to now try to use this insight to return to this original puzzle for the infalling observer in the black hole that I asked in the beginning. There is a question by Dongseng. Given the time, Dongseng, do you mind if I take your question in 5 minutes?
Sure.
Thanks. So now we would like to turn this logic around. So far, we try to we assume knowledge of the system at the initial and final slice, and we try to extract physics in the frame of the probe along its journey through the bulk. But now, of course, our ultimate goal was to actually construct that generator of the proper time from first principles in order to apply it in that situation of a probe falling inside a black hole. Now, we haven't gotten there yet, but up to these corrections that I was describing, this proper time will be the modular flow. So let's try to use this insight and see how far we can get for this puzzle of the infalling probe. So we go back to this two-side setup. We have two CFTs, one left and one right, decoupled in some initial thermophile double state. We introduce a probe. How do we do this? Well, in our formalism, we have to take a subsystem of the CFT and entangle it with a reference. Now, any procedure of that type would look like this. We have a thermophile double between left and right CFT and some reference in some fixed initial state. And then we apply some unitary that couples the right and the reference. Any entangling procedure would look like this. But the important thing is that we don't touch the left in this process. This unitary does not touch the left. Now, according to the rules that I try to advocate for, the proper time evolution will be given by simply up to these corrections will be given by the modular flow after I trace out the reference. Well, the observation that we found noteworthy in this setup is that because of the pre-existing entanglement between left and right, when I construct this state and I trace out the reference, then the modular Hamiltonian I obtain couples left and right. So it's a naturally two-sided operator. And of course, using it to propagate along this borderline will eventually map an operator in the right that originally was in the right CFT algebra to a operator that has support on both CFTs. thus naturally resolving this puzzle that I forgot to mention that the first place I saw, I learned about this puzzle was from Marolf and Wall. Now, this is not a resolution of all aspects of black hole interior puzzles, but of all puzzles in the black hole interior, but at least it explains that question that I originally tried to ask. In what sense, in the reference frame, in what sense the entanglement of the initial state of the two CFTs translates in the reference frame of the excitation translates into a coupling between left and right. We did not construct, we did not assume that coupling, we kind of derived it from the set of rules that I tried to advocate for. So I think I'm running out of time. So I just wanted to mention, there's a way of being a little bit more explicit about this, about constructing this infalling observer's Hamiltonian. If instead of using thermofield, a black hole falling inside a bigger thermofield double, if instead we analyze the problem of a black hole crossing a ringular horizon, and there you can be relatively explicit about the little cartoon I explained in the previous slide, where you can show that the modular flow of some atmosphere operator at this close to the black hole initially, after I evolve with the modular Hamiltonian, you can see that it ends up being an operator on a right CFT operator conjugated by some amount of translation along this null slice, along this null ray, which is precisely the effect of that is responsible for shifting that guy behind the horizon. I just want to emphasize, however, that this does not resolve all problems with black hole, with the black hole interior. In particular, it suffers from the frozen vacuum for people who are familiar with this, with obstacles in interior reconstruction. I don't have time to comment on that. There are some ideas that Jan de Boer, Daniel Jaffers, and I are currently exploring for resolving that final puzzle. But at least the formalism I've given you here, I hope at least, is a first step towards understanding that internal notion of time. We didn't go all the way precisely of that frozen vacuum issue that we didn't resolve, but at least it gives a guidance for how to think about the evolution in the frame of an internal excitation, a question that seems to be important in quantum gravity. In our formalism, the way this dynamical clock emerges is precisely by tracing out the microstructure of the observer themselves and obtaining the reduced density matrix of the rest of the universe after we traced out the observer. This is kind of what generates that local notion of time. So it's an interesting question to explore whether this somehow is close to what we ultimately will think of time in more general contexts. And with this, I will end and open it up for questions. Thank you for your attention.
Okay, thank you. Dongshen, go ahead.
Oh, yes. Thanks for the talk. The question I have is regarding like the main formula you have in one of your slides.
Yeah.
And I'm curious about, because you have some atmosphere region, and I'm wondering why your formula here doesn't really depend on your choice of your atmosphere region, like how large it is or how small it is.
Well, this is supposed, okay. So the precise objects appearing in this formula does depend on assumptions I make about the structure of the spacetime close to the black hole. Namely, I'm assuming that the spacetime close to the black hole looks like a black hole spacetime. So the appearance of this, the reason why this this modular flow generates a Schwarzschild time, and why the effect of the infalling excitation is captured by the scrambling mode are, in fact, directly dependent on the fact that the atmosphere region looks like a black hole. So it doesn't depend on the size because, well, this formula is supposed to give me the generator of proper time for the atmosphere fields. So of course, this will break down as I keep going further out and out from the black hole. At some point, it will break down. But the point is that within its regime of validity, the proper time operators will be, the proper time evolution of the atmosphere operators will be generated by that guy.
Okay, so the validity of your formula depends on your choice of the size of the atmosphere.
It will break down if you go far enough, but also if you go far enough, there is no canonical kind of way of, it's not really meaningful to talk about propagating degrees of freedom along the world line of the black hole. You have to choose a slice at some point. So it's ambiguous how exactly you propagate things far from your world line in your proper time.
Okay, thanks.
Ping.
Hi. I have a question. Though you haven't not okay, you choose to skip the frozen vacuum, but I'm quite interested in that part. Maybe you can expand around that. Basically, I read your paper, but I found that I think so it seems you would like to say that if you cannot if you do not allow the observer the probe black hole to get close to ADS boundary in the final time, then you will have the frozen vacuum. Why that is the case? Does that mean that you have to deal? It's very hard to deal with the like a collision behind the horizon issue, right?
So, okay, good. So two statements. So the proposal, the first part of this talk does not suffer from the frozen vacuum because the setup that we used was we initiate the probe, we have access to the probe black hole and its atmosphere at the initial and the final slice. So, and then so this provides us for us as an input, the unitary that relates these sets of operators. And then all we have to do is just extract the physics in the frame of the black hole. And then we have proper time and energy distribution measured by the appropriate coefficients. That doesn't suffer from the frozen vacuum. I can detect whether particles were absorbed along the way precisely by the coefficient of this scrambling mode over here. However, if we want to propagate behind the black hole horizon, we shouldn't allow access to the probe at the end, right? Because then we would be inputting the problem that we want to solve. And for that, you would have to predict this coefficient of the scrambling mode before you fall in the black hole from the initial data. So that is at least one aspect of that story. Of course, then you have to worry about these other corrections as well if you want to really reconstruct everything along the trajectory. But the reason why this formula, as it stands, does not resolve all questions about the interior is precisely because of this issue. That you will have to somehow have a prescription that will tell you what's the coefficient of this, what's the scrambling mode contribution using initial data. And we didn't provide such a prescription. It doesn't mean that it exists, but we didn't provide one.
But what you say that this F depends on data from both sides, from the left and the right?
Ultimately, it will have to. Yes, you're right. But the point is, is there a nice kind of simple prescription for obtaining that data using, what's the most kind of economical way of extracting that data from the initial slice? If you have that, then you have the ability to. Well, that is essentially answering the question of whether there were particles crossing paths with my infalling probe, right? So extracting that information is really addressing the frozen vacuum, if there's a way of doing that.
Isn't the answer that if you send signals from the left, you will have different Fs here? And
yeah, that's right. Yes, of course, that's exactly what's going to happen.
But I don't see why there is a. So in your formalism, wouldn't you find a different F? I mean, you expect a different F, but you wouldn't your formulas lead you to a different F? This is what I'm asking.
Yes, good. So the formalism, as I presented it up to this point, is a formalism for inputting the initial and final. You have access to the probe at the initial and final times, and then you extract what happened along between these two times in the frame of the black hole. So that's why this particular formalism as presented here does not answer that question, because I would have to input the atmosphere operator algebra in the interior.
I see. I think that the formulas depend on reconstructing the operators behind the horizon. I mean, reconstructing the operators along that slice. And so in this, if it is a black hole that is falling behind the horizon of a bigger black hole, you would have to reconstruct the operators inside.
That's right. I would have to input the interior operators in order to reconstruct the observer, the experience of the observer. So that's why, in the way that this is phrased, does not address this question directly. So an extra input is needed. That's, I guess, some extra input is needed in order to pin down. Ultimately, we want to get, and that's kind of perhaps what I should be emphasizing most, is that it's an important question to understand. If I introduce a physical probe from the right, what is the generator of this internal clock of the observer? If I know how to propagate along this observer's world line, then I can answer these questions. So we made a step here, but we didn't go all the way, and there are remaining questions of how exactly. Somehow the missing element seems to be some sort of requirement of locality. But I have comments to make about this, but I think this is not the proper time and place to make them.
Okay, I see. Thank you. So could I understand that in the way that, say, if you can access the final initial and the final atmosphere operator, so you all know the left hand side, and you can read the coefficient f and to know whether it's absorbed. But if you cannot access the final slice, you have no idea about left hand side, so there is no way for you to read out anything, right?
That's right. So to put it in a different way, I would be able to reconstruct the experience of an observer that traversed the wormhole, like using your protocol, for example.
Yeah.
But I wouldn't be able to address the experience of an observer that just fell in the singularity. At least not at the final stage of the development. I should emphasize that Daniel, Jan, and I are working on resolving this issue, and there's a couple of ideas we're exploring. So hopefully we'll have something to report soon.
Mm-hmm. Thank you.
Josh?
Hi, I might have just missed something, but I was wondering if you could clarify what it means when you talk about the pro-black hole going past or in the horizon, or falling into another black hole's horizon, maybe just classically, because if one small black hole went into a larger black hole, you wouldn't say that small black hole continued to exist inside the larger black hole. They'd just have merged. So I don't really know what it means for the pro-black hole. Yeah. Right.
So yeah, good. That's well, I agree that from the external perspective, that's what it looks like. But if you have a big, huge black hole and you're also kind of infalling together with the infalling black hole, I don't see the horizon as being a special place for your observations, right? Of course, the space-time from the exterior for any probes that live in the exterior will ultimately look like a bigger black hole of a bigger size. But if you have a small probe black hole falling and you're falling together with it behind the horizon, I think that you will continue seeing a black hole. No?
So you're defining the black hole region relative to another probe that's falling alongside the black hole, or? I'm
just referring to. So there's nothing. For example, let's say that I'm just saying that there's a question of the frame in which you're describing that space-time. For these purposes of an infalling observer, it looks, or at least it seems to me that in the infalling frame, there's nothing special happening at the horizon. So
I think this would be true in flat space. I mean, in asymptotically flat space, this is clearly true just by, the locality. You can never tell if you're falling across the horizon of a large black hole. It's a little less clear in anti-de Sitter space because the time that it takes to reach a singularity is just the ADS time scale. And your small black hole is also the ADS timescale.
Yeah. Okay, I'm implicitly having, thanks for the comment. I am implicitly having in mind that I have pushed the formalism even further to accommodate smaller black holes, as I kind of commented at some point, although there are some subtleties to be understood in that context as well.
Okay.
Thank you.
Oh, sorry, you were saying something more? Okay.
No, just thanks.
Lampros, I understand why you want to use black holes, but let me offer a different narrative and see if you agree. So I would find the story that would make slightly easier understanding is you make a localized wave packet of some scalar, which you would say initially you reconstruct, let's say it's in your causal path, so you reconstruct it using HKLL, and then you evolve it into using its own sort of proper time. And then you can track that evolution either by using, depending on where it is, modular evolution or some kind of causal evolution. And now we could even relate this back to your story by trying to think of this picture in the word line formalism for this wave packet, and try to use some kind of if the scalar is sufficiently heavy, think of a first quantized word line picture where you sort of think of the effective field theory from the word line point of view, and then ask the question you're asking. What aspect of the black hole do you think was, would A, first, do you agree with this? And B, if so, don't you think this is simpler than keeping track of the small black hole and associated issues having to do with, how small do you want to make it to avoid backreaction, et cetera, et cetera?
Yeah, so this is a question that I don't know the final answer to. The black hole has many, as I said, convenient features, and the most important thing for this formalism is that I know how to describe in the CFT this generator of the boost symmetry close to the horizon. That was that was an important ingredient in the story that I presented. That I had some handle on that on a clock close to my probe. Now, was this a convenient idealization that allowed us to probe the spacetime, or is it something deeper? Is there a kind of a way of extracting this universal information about the probe? As I said, it's kind of declaring maximal ignorance about the nature of the probe given its mass. So I don't know. I'm agnostic to this question. I was initially also hoping that there would be a prescription that applies to any probe, but maybe that's the wrong question to ask. I'm not sure. It's definitely worth exploring this question, but I don't know the answer. Thanks.
Sorry, I have a quick comment. Wave packets, they tend to spread in space as you involve them in time. So.
Right. Yeah, that's another problem with the wave packets. And in fact, that's also a problem, unfortunately, with small black holes as well, because if you have a very small black hole, its wave packet will also spread. So it seems like any sub-ADS probe will eventually, like this that's actually the subtlety with these microcanonical black holes that I commented on, that they actually describe a black hole whose center of mass is, the location of the center of mass is uncertain within an ADS radius, precisely because of that spreading. So one has to inevitably deal with this. Thanks.
Alexei, I agree. I just wanted to say that you could make something like a localized piece of rock that's like an asteroid that probes the geometry, but I wanted to use the scalar as an analogy. Thanks.
Sorry, Matt, did you want to ask a question? Matt Hedrick?
Yeah. I have a very elementary question from the beginning of your talk, Lampros, that I got immediately confused at.
Oh, no, you should have asked it then.
Well, a lot of people were asking questions and I wanted to let you finish the talk, but you seem to be treating the atmosphere as a closed quantum system, and you described a time evolution operator that was unitary, but of course the atmosphere is an open quantum system. Is that just some negligible correction to the story you're told? Or, I mean, it seemed, yeah, why can I pretend like the atmosphere is a closed system?
think he's using the hypothesis that if you have a black hole and you describe it from the outside in the full exact description, it's a complete system, right? You're worried about things falling into the black hole, or
well, things can cross in and out of the atmosphere from the rest of the space-time.
Yeah, I don't think you can have it both ways and say that it's a probe and yet say that it's not an open system. I think this may be related to the fact that you're restricting to one scrambling time. During that time, you basically recycle one set of modes in the atmosphere.
Isn't his definition including all the fields outside the black hole at some instant in time? I mean, the most relevant ones are in the atmosphere, but in principle, you could include everything.
Yeah. So so the point is, if you have so if you have the initial atmosphere operators and you act with them in the modular flow in order to obtain the final atmosphere operators, then clearly the final guy will have support over a large region of space-time. The point is that this, together with the scrambling mode, will capture the dominant contribution to that final operator, up to corrections that are transient. That's kind of the statement. So it's not that, so I'm trying to say here's a set of operators at the initial slice, and here's a final set of operators at the final slice near the black hole. And I want to express the final ones as a particular flow of the initial ones. So that's, it's kind of like, so of course, once expressed in the Schrödinger picture, once the final operators are expressed in terms of the original operator on the operators on the initial slice, then of course they're spread out over the entire universe, or a big region of it.
Okay, so really we're not really restricting to the atmosphere then.
So I'm only using so the restriction to the atmosphere is I have a final set of operators that I want to express as a particular flow of the initial set of operators. Did that make sense? So of course, the operator that I act with, the flow that generates the flow, is a non-local, is an operator that will of course spread out the support of the operators.
So could I have a more complete description with some Lindblad operators or whatever formalism, and then you're just saying that I'm just throwing away that part?
Yeah, the part that there are these effects here that that decay because of this quasi-normal decay in the black hole atmosphere. So this was important in order to kind of cleanly extract the important contributions and make some progress in constructing that generator. But of course, ultimately, these transient effects need to be accounted for, and I did not here.
I see. Okay.
Any other question?
There's a hand raised.
I might just, I'll make a comment on the people who are asking about using particles and the spread of the wave function. I think this isn't a problem if as long as your mass of your particle is large in ADS units, then it's effectively, ADS gives you a harmonic potential, which means the width of the wave function is like the geometric mean of the Compton wavelength of the particle in the ADS scale. So that can be as small as you like, as long as you take your particle to be heavy. So I think that is not, in principle, an obstruction to using that kind of method.
Right. Yeah. Thanks for the comment. Yeah, that's right. I implicitly had in mind this kind of state here, where I want, because I'm kind of for now committed to this black hole probe, and when I write down this state, of course, this microcanonical thermoplane double, I can of course describe a smaller black hole, but because this is an equilibrium state on the system side, then it actually takes the equilibrium state of that small object will be completely uncertain. Its location will be uncertain within an ADS radius because of that spreading of the wave function. So it's kind of like the long time limit, if you will, of the state of the particle. So while you're right, if you can kind of use that method for massive particles, then there is no problem. But if you want to kind of use this approach for describing the probe, then you have to deal with it. And I don't
Why
yet
are
know.
you asserting that the small black hole spreads out? I mean, if you make it much, super Planckian, but smaller than ADS size, then it just stays put for, I mean,
if you wait long enough, all wave packets spread, right? The small black holes is
an ADS.
No.
The point is that it doesn't in ADS because the ADS potential, there's effectively a confining quadratic potential, and that keeps the wave function much parametrically narrower than ADS scale.
Right, we will be within an ADS scale, but if I want to describe a sub-ADS black hole, a black hole that's much smaller than LADS, then it sees effectively a flat spacetime around it up to the ADS scale. So the statement is that the wave packet of this black hole, no matter how classical and massive it is, eventually it will spread out over this entire ADS radius. And because of this kind of microcanonical equilibrium state, it can be thought of as kind of the approximation to the long time evolution of that probe, then its center of mass position will be uncertain within that radius.
Yeah, and the point I'm making is that's not quite true in ADS. If you're that's only true if your mass is the same order as ADS scale. And actually, if you look at the width of the wave function of a particle with mass that's larger than ADS scale, then it's like the square root of the Compton wavelength times the ADS length. And if the Compton wavelength is small ADS units, then it's much smaller, so you can see it at sub-ADS scale.
Right. Yeah. So for big black holes, it's not a problem. I agree. But for small black
I would say if you take like hundreds of an ADS-sized black hole, it will survive much longer than ADS timescale. So it will cross your Rindler horizon, no problem.
Yeah, if you have a black hole whose mass is 1 million, okay.
We can discuss this a little bit.
I think I would like to make a comment, or maybe agree. So these formulas. So your formula for the time assumes that you have some access to the bulk operators, right? So in principle, you could have followed a different prescription. I mean, which would also give you time, which would be to create a wave packet of a massive particle with one bulk operator and annihilate it with some other bulk operator in the future. And that 2-point function then contains e to the I mass times t, and then that would be some other way of extracting the time from the face of this wave function. So do you agree that this is more or less conceptually similar to what you are doing, perhaps less universal, but also it highlights the problem that in order to get to the black hole interior, you need to have access to these operators in the black hole interior?
Yeah, so it is conceptually similar. It is less universal. So the part of the motivation of trying to, it's important to keep in mind that what we were trying to do ultimately was to understand what are the principles for constructing that proper time Hamiltonian directly from the quantum system. So while we had to make a retreat in order to make progress, and we had to kind of, we retreated to extracting the physics in the frame given initial and final slice information. Ultimately, what we wanted to learn was how would I build that proper time Hamiltonian from first principles? And we made some progress I want to believe that we made some progress in that direction, but we didn't go all the way. And because there are some ingredients missing precisely related to this problem that you're referring to. So it is, of course, it is conceptually similar to the phase that the particle acquires as it propagates through the bulk in this way. But in the process, we built an operator that propagates degrees of freedom along that word line. So I think we made a step a little further. We wanted to propagate things along that word line. So I hope this kind of clarifies the perspective that we're taking and why we went into trouble.
Thank you. That's it. Henry, do you still have a question, or?
No, I think we can.
Okay.
Yeah,
well,
thanks.